Alright guys, so in this video we're going to talk about an important term called differentiability. So this is a definition we're going to see throughout the year. It's an important term for sure. I want to define it and give you some examples of how it's used and kind of think about that. So we're going to first say a function f of x is differentiable. Function f of x is differentiable given there are two cases that must be true. Is one, f of x must be continuous, and then two, the derivative, as you'd expect from differentiate, the derivative f prime exists is defined. And we could also think about that from the limit perspective and saying, like when you take that limit as h goes to 0 of this slope, that limit exists and is the same on both sides. Okay, so what we're basically saying here is if a function is differentiable, and this could be either on an interval or at a point, two things must be true. One, it must be continuous. Two, the derivative must be defined. So if I tell you a function is differentiable, you know it's continuous. That actually is pretty useful. So let's talk about graphically what this looks like. So if you have a differentiable function, and these are like functions you feel pretty comfortable with, right? Like a straight line. It's a continuous function, the derivative exists. You could have like a sine wave or something. The derivative exists at any point. Even something a little like shoop-de-whoop like that, those are examples of something that would be differentiable. Now, if something is not differentiable, there are two different ways that could happen. So if it is not differentiable, well, one thing is it could fail the first condition. So it could be not continuous. So we've seen plenty of examples of what not continuous looks like, right? Maybe you have a jump in your function. Maybe you have an asymptote at some point, like a vertical asymptote. So it's not continuous at the asymptote or the jump or the hole, which means that it's not differentiable either. But there's another case that I think is actually new, and this is more interesting. What if a function is continuous but not differentiable? So if the function is continuous, but that derivative, I should spell the word right, but that derivative does not exist at some point. So f prime does not exist. And there are two basic ways that this could happen. One of them, which is relatively uncommon, is if you have, say, a couple semicircles that are kind of sliced together. So if you looked at this point, this dy dx is undefined because it's a vertical tangent line, and a vertical tangent is undefined. Now, the other case that I think is far more interesting, that we can be continuous but not differentiable, is something called a sharp corner. Okay, in a sharp corner, you see this on an absolute value graph, but it looks something like that. Okay, so at that point, the function exists, right? F exists. But also at that point, it's not differentiable. F prime does not exist. So this makes sense, right? If you try and draw it, like how do you draw a tangent line through that point, right? Do you make it like that, like that, like that? Like all these tangent lines just go through at one point. So none of them actually work. You cannot draw a tangent line. But also, think about what's happening to the derivative. So if we think about like the slope at this point, from the left, that f prime approaches, say, -1. From the right, that f prime approaches +1, right? Or I guess it looks like about 2 in this case. So we have a slope here of like roughly +2 going up. So because these are different on both sides, they're not like both approaching 0 and both approaching 3. Because these are different on both sides, that limit, that f prime, does not exist. So in any of these cases, whenever you see, whether it's like a sharp corner like that, or you see like a shark fin type thing where it turns quickly, or maybe goes like that and then flattens out. In any of these cases where you have a sharp corner, that is not differentiable. And again, that is because the slope approaches two different values from the left side and the right side. Okay, one more thing I wanted to do is just kind of an example of a problem. I might ask you, for example, say g of x equals 2x plus 1 if your x value is bigger than 1, and x squared plus 2 if your x value is less than 1. And I might ask you, is g of x differentiable at x equals 1. Okay, so there are two things you need to check corresponding to the two things. First off, you're going to ask yourself, is it continuous? And then, is the derivative defined? Does it look the same on both sides? And I think that's actually something you want to think extremely importantly about. Okay, so first off, we're going to ask, is it continuous? Okay, so that's where we take the limit from both sides. So if we want to find g of 1 is just the top case. That's equal to 3. If you want to take the limit as x approaches 1 from the positive side, that's still 3. If you want to take the limit as you approach from the negative side of your g, you get 1 squared plus 2, which is 3. Okay, so it is continuous, right? The limit equals the value of the function there. We're good. Now we're going to ask ourselves, what about the derivative? So what I'm going to do is I'm going to check g prime on both sides. So my g prime here, I could take the derivative of each part. Derivative of 2x plus 1 is 2 for my x values greater than or equal to 1, and it is 2x for my x values less than 1. So I'm going to do the same thing that I did with continuous. I'm going to plug in that 1 on both sides. So as I take that limit as x approaches 1 from the negative side of g prime, that's 2 times 1, which is 2. If I take the limit as x approaches 1 from the positive side of g prime, again, I just get 2. So good. So the g prime is the same on both sides. So we have the slope is the same. We know it's continuous, so it is differentiable. And again, both of these must be true. If it's differentiable, but you get different values here from the left side and from the right, oh, that's a bad color, from the left side and the right side, if those are different, it would not be differentiable. Okay, so that's what you mean by the term differentiable. Hope that helped, and I'll talk to you guys soon.